In this lesson, we're going to look at product, quotient, and powers of complex numbers using the Euler's form. And we will know why it is so easy to operate in the Euler's form or the polar form of numbers. So let's look at two complex numbers. Z1 is R1 cis theta 1, which means I can write this in the Euler's form as R1 e raised to I theta 1, and Z2 is R2 cis theta 2, which is R2 e raised to I theta 2. Now if I have to multiply these two numbers, right, Z1 times Z2, if I do it in the Euler's form, it's very intuitive to understand what is happening. The base is the same, so I can multiply the modulus together, and for the indices, because the base is same, the indices get added, which means the modulus is simply product of the two and the argument is the sum of two. So the modulus is the product and the argument is the sum. That's what is happening here. So very intuitive to understand that arguments will get added, correct? What happens then in the case of division? So let us take the same number. So if it's Z1 divided by Z2, so it's R1 e raised to I theta 1 divided by R2 e raised to I theta 2. Again, modulus, if it's division, it will get divided. But what happens to the argument? This time the arguments get subtracted from each other. That is how the division and multiplication can be understood. I'll show it visually how it looks like using Desmos. So I'm starting with two complex numbers. Z1 is 1, 1, which means one real part and one complex, and Z2 is minus 1, 1. So let's find their argument and their modulus, right? So that I'm convinced that what I'm getting, the answer is correct. So 1 plus I will have a modulus of root 2 and an argument of pi by 4. And the other number is minus 1 plus I will have the same argument, modulus, but what will be the argument? Remember, it's in the second quadrant. Second quadrant with the same kind of orientation as the number. So this is pi by 4. So it's pi minus pi by 4. We had discussed this when we looked at the Euler's form. The two numbers 1 plus I and minus 1 plus I are symmetric with respect to the imaginary axis. So the argument will be 3 pi by 4 based on this particular representation. And so the product will be root 2 times root 2 is 2. So the modulus will be 2. And the argument will be addition of the two individual arguments, which will be e raised to I pi, which means it's a real number on the negative real axis. Is that what is shown here? Absolutely yes. Minus 2 comma 0. So the modulus was 2 and the argument is pi. That means it will be minus 2 because cos of pi is minus 1, sine of pi is 0. So no imaginary part, only real part. So what we did is indeed correct. I am able to see that. So let me change these numbers. So if I'm changing the modulus, what is happening? Obviously modulus is simply multiplication. So if modulus is becoming bigger, then the modulus of the product also must become bigger. Okay, fair enough. What happens when the argument changes? If argument is changing, see how it is getting rotated by the same amount because it is sum of the two angles. So if I have this number as completely imaginary, okay, let me have this here, and this number is completely real, then what should the argument be? The resultant argument should be pi by 2 plus pi, 3 pi by 2, and that's what we are seeing here. This is not completely real, that's why. So now, see, a number which is only imaginary times a number which is only real resulted in a number which is only imaginary, with 3 pi by 2. So I'm seeing that the argument is indeed getting added. Now, so it's very easy to imagine the multiplication as simply the division as simply multiplication by the reciprocal. And so the division of subtracting also makes a lot of sense. So I can think of division as, so z1 divided by z2, correct? Which means r1 e raised to I theta 1 upon r2 e raised to I theta 2. I can think of this as r1 divided by r2. This is okay. I can think of this as multiplication by minus theta 2. So I can still think of them as addition, but addition with a negative angle. Correct? So r1 divided by r2 is the modulus, and e raised to I theta 1 minus theta 2 is the argument. Now what about powers then? What happens when z1 is raised to n? So what is z1? z1 is r1 e raised to I theta 1. So if that is raised to n, by laws of indices, I should get r1 e raised to I n theta 1. Which means it will become r1 cos n theta 1 plus I sin n theta 1. This result is called the de Moivre's theorem. It connects that the powers of a complex number will change the modulus by the same amount, but the argument gets added. So look at r1 raised to n means what? It's like a geometric progression, right? r1 times r1 times r1 is being multiplied by the same ratio. And n theta 1 is like theta 1 plus theta 1 plus theta 1 plus, so added by the same amount. So like an arithmetic progression. So the modulus is changing like a geometric progression, and the argument is changing like an arithmetic progression. So what will happen if I have, for example, if I have 1 plus I raised to n, which means square root of 2 raised to n, not 2 raised to n, and what happens to the angle? Cos of n pi by 4 plus I sin n pi by 4. So it will be pi by 4, then 2 times pi by 4, which is pi by 2, then 3 times pi by 4, then 4 times pi by 4, and so on. That's how the, and where will it rotate? Well, it will rotate on a circle. Initially it will be, if n is 1, the circle will have a radius of root 2. When n is 2, it will have a circle of 2. When n is 3, it will have a circle of 2 root 2. So it will go on, the circle will go on increasing in the radius, but the angles and the angle will keep changing as a arithmetic progression. So pi by 4, then 2 pi by 4, then 3 pi by 4, then 4 pi by 4, and so on. That is how we can imagine the product. So the modulus, if you want to see the powers also, when a radius changes, they come on a bigger or a smaller circle depending on the value of the radius, correct? The number changes. And what happens to the value of the point rotates as theta changes? It rotates on that circle based on what the radius is. So that's how we can understand the powers of a complex number, which is also much easier to understand when I look at the Euler's form than any other form. Correct? Doing it, so for example, if I have to do 1 plus I square in a Cartesian form, I'll have to do 1 plus I times 1 plus I, which is 1 plus I minus I square, 1 plus 2I minus I square is, plus I square, and I square is minus 1. So 1 and minus 1 get cancelled, and answer is 2I. So I know that it is resulting in only a complex number. If I think of it as a Euler's form, then look at how easy the multiplication is. I know that the modulus gets squared, which means 2. The arguments get added, which means pi by 2. That means the number is only on the imaginary axis, which is 2i. So that's why the Euler's form is easy when it's product, quotient and powers.